Good evening and warm greeting to all of you present here. It is endeavored to make the contribution towards achieving academic excellence. St. Joseph College of Engineering takes an immense pride in organizing the international webinar Solar to Hydrogen Fluid Generation. I am very happy to mention that our department stepping again into the next step of success. Now, at this juncture, I am A. Mahalakshmi, Department of Science, St. Joseph College of Engineering, would like to thank each and every one of you for being here with us today. First of all, I thank the Lord Almighty for making this webinar a great success. I happily extend my heartfelt gratitude to our chairman, St. Joseph Group of Institution, Dr. B. Babu Manoharan sir, for his guidance in making this webinar a resound success. It takes this opportunity to thank our beloved Managing Director, Mrs. S. Jessipriya Madam, Director, Mr. B. Sashekhar Sir, for supporting us in all the way they can. I would like to acknowledge my sincere thanks to our respected Principal, Dr. Vatti Seshagari Rao Sir, Dean Dr. B. Parvada Vardini Madam, for always supporting us in all we do. Our head of the department have been encouraging and very supportive throughout the planning and implementation of this webinar. We as a team would like to thankful for the convener Dr. V. N. Nandini Devi ma'am. To be inspired is great, but to be an inspiration is an honor. It's a very great privilege to welcome our most valuable chief guest, Dr. Sudhagar Pitchaimuthu, to his grand online seminar. With a joyful heart, it's a great honor for me to welcome you, sir, to be a faculty here with us today. Your participation as educator is greatly needed to enrich the life of many students. Thank you all for the support and participation. Have a great session ahead. Now I welcome Dr. S. Rama, Assistant Professor of Physics, to introduction our chief guest.
Good afternoon to one and all present here. On behalf of our institution, I am Dr. S. Rama, Department of Science, St. Joseph College of Engineering. Welcome the keynote speaker, Dr. Sudhagar Pitchaimuthu, to share his valuable experience and knowledge in this webinar. Welcome, sir. It's a great privilege to share of his research and professional experiences among his intellectual group. Dr. Sudhagar Pitchaimuthu is a Sir Kimbrough Rising Star Fellow awarded by European Regional Development Fund through Welsh Government. Also, Sudhagar is a Royal Society of Chemistry. Currently, he leads multifunctional photocatalyst and coating research group at Specific Material Research Center, College of Engineering, Swansea University. His research background is on nanomaterial synthesis and coatings for constructing low-cost solar energy conversion systems. His research mainly focus on how transforming the abundance sustainable solar energy into multifunctional applications such as energy conversion devices. Success counts a lot. Yes, he succeeded. He was the recipient of prestigious JSPS award and working as a JSPS research fellow under Professor Akira Fujima at International Photocatalytic Research Center, Tokyo University of Science. Dr. Sudhagar secured approximately 800 pounds in equal to 7 crores in Indian money grant as a principal investigator and co-investigator. Dr. Sudhagar has been published 92 articles in peer-reviewed international journals. His H index is 32 and contributed 6 book chapters. Also, he has presented more than 50 articles in international conferences. Dr. Sudhagar is keen on delivering invited talks and engaging public events. He has been delivered more than 40 invited talks around the globe. Dr. Sudhagar served as a panelist for role of Indian diaspora in capacity building for affordable solar power led by Honorable Prime Minister of India. Recently, Dr. Sudhakar's discovery of T-leaf mediated quantum dots in cancer cell diagnosis and treatment received world attention through popular medias like BBC, Nature Outlook, Extra. And also, he is the founder and chair of ANEH conference series in view of helping Indian rural students research and innovation. He has established ANEH conference series and organizing international conference and hands-on experience workshops on nanoscience and technology. Apart from research, Dr. Sudhagar is fascinated science writer in Facebook and blogs. I would proudly say that this is not the end and just a beginning. Yet a lot more to share his rocking achievements, but due to time constraint, I end up with this great introduction.
Rama, shall I start?
Yes, sir.
Okay. Thank you very much for the nice introduction, Dr. Rama and Dr. Mahalakshmi. Could you check my voice is audible?
Yes, sir. Please wait one
Okay.
minute, sir.
Yep. Okay. Shall I share my screen?
Ashari, yes, sir.
Okay. One second. Okay. So, okay, go. Sorry. Can you see my screen?
1 minute, sir. 1 minute, sir, please.
Sure, sure. Okay. I think
Sir,
it's still
share your
take.
screen, sir,
Yeah, yeah.
because
I
it's
already no,
no
already I shared.
share because my side net is there is some problem in my network.
Okay. Is there any?
1 minute, sir.
One second. I will stop and share again.
Okay, sir.
I think there is a problem from your side. Is it possible to change the
Yes, yes, sir.
host instead of you, and someone can host?
I'm not able to view my screen, sir. That is a problem. I'm
Okay,
not able to view my screen.
can I stop it? Can you stop the sharing?
Yes, sir.
Okay. Don't get tension. You just ask your colleague to change the host. Okay, then we can.
Ma'am, what happened?
Ma'am, my side net is not working, ma'am. It's rotating. I can't able to
Ah,
do anything. If I close the StreamYard, or shall I close the StreamYard?
no, ma'am. The link will be changed. No.
Yes, ma'am. That's why I'm waiting for my net. So I'm not able to.
Okay, I guess there is some technical problem from the organizer side. Okay, I think meanwhile I will take an opportunity to interact with the viewers or delegates. So I'm Sudhakar, as a speaker introduced. I'm from Swansea University, UK, and this is one of the top 50 universities in UK. And basically, I'm working on solar energy conversion system, starting from the solar energy conversion to electricity to fuel generation, water treatment application, and chemical synthesis. And it's a kind of diverse application from start from one end to another end. Okay, and uh, before going get into my talk, I would like to introduce about my career in India, then how I transformed from India to UK. Uh, I was started my research in Coimbatore, Kongunadu Arts and Science College. It's under Bharatiya University. I started in semiconductor physics area. Basically, I have a strong expertise in quantum dot semiconductors. So initially, I tested with these kind of quantum dots in photo conduction studies. Then I was seeing some of the interesting property. Then I applied the kind of visiting fellowship in South Korea. Then I got an opportunity to work in Hanyang University, which is located in Seoul, and I transformed my quantum dot research into quantum dot solar cell. So that is a very interesting part in my career as well as in my research. So I got some very interesting results in quantum dot solar cell. For example, those days I did my PhD around 2008 to 2009. I completed my PhD. So that time, these kind of quantum dots, it shows a less than 1% efficiency, but it have a strong potential to go in a high level. But during those days, the efficiency is very, very less, compared to Dyson solar cell or any other silicon solar cell. So almost around 3% I have achieved. Then I have seen another interesting area, these quantum dot materials, how to apply in a solar energy conversion to fuel generation. Okay, so then I have applied the JSP's fellowship. So with this record, then I got a opportunity to work with Professor Akira Fujishima, who is the original inventor of photoelectrocatalytic water splitting into hydrogen and oxygen. So then this great opportunity, give me to learn what are the fundamentals in photoelectrocatalysis and how to scale up the system. Then during this journey from India to India to Korea and Korea to Japan, so almost I have published more than 70 research articles, and a few of the patents are in pipeline. Then I got an opportunity in 1 million project in European Union. It's called European Regional Development Fund. It's hosted by Swansea University and Welsh government. So now I'm in Swansea University, UK. I setting my own research group. So it is called multifunctional photocatalyst and coatings group. So this is my research travel, how I travel from the east to west. Probably today in my presentation, I'm going to show you what are the fundamentals of photoelectrocatalysis and what are the challenges in this field. And suppose if someone want to work in this field or collaborate in this field, so what are the challenges in this field? You have to know it. That's very important. So this is my idea of the talk. Give an introduction about the field, as well as what are the challenges in this field, and what are the advantages, or how the field is going in progress in future. So in three aspects, I will cover my talk. So hopefully,
Excuse me,
yes,
sir.
yes, please.
Can you again share
Yeah,
it,
sure.
sir?
Yeah.
Uh,
1 second. Okay. Yep. Okay. Okay. I shared my screen. So can you see my? Can you see the screen?
yeah, just a minute, sir.
Can you see this? Can you see my screen?
No, sir.
Already I shared.
Not yet.
I already shared.
Not yet,
Okay.
sir.
Okay.
Not yet, sir.
So, I think there's still technical issues going. Let's see. Uh, I would request the participants. There is some technical issue in the organizer side, but they are taking some serious steps. Could you please wait a few minutes, 5 to 10 minutes? It would be great to support them. I know this is a pandemic time. There are some kind of unexpected issues. It comes from any end. So we try to support them. We will stay with them few minutes, like a 5 to 10 minutes. Let's try to fix the issue. Thanks for your patience, okay? Because I'm sitting in UK, I can't help you, directly. But however, I'm keen to share my knowledge and to our community. So please wait few minutes, okay?
என்ன கொண்டாந்து என்ன கொண்டாந்து உள்ள போட்டாங்க. Good afternoon, sir. Good afternoon, sir.
Hello. Yeah, that's awesome. So, okay.
Sudhagar, sir. Good afternoon, sir.
Can you hear me? Yeah. Yeah. Good afternoon.
Fine, sir.
Okay. One second.
Yeah, I can hear you, sir.
Hello. Can you hear me? Hello.
Yes, sir.
Yes,
Yes,
sir.
sir.
I
We are
can hear
hearing
you,
you.
sir.
Okay. Shall I try my screen again? Share
Yes,
the screen
sir.
again.
Yes, sir. You just share your presentation, sir.
One second. Okay. Okay. Let me know once it's shared.
Yes, sir. We are getting, sir.
Okay. 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 Shall I start?
Yes, sir.
Okay. Okay. I'll set my alarm.
Yes, sir.
Okay. Okay. Please mute your mic. Okay. Then I will start. Okay. Okay. So sorry for the inconvenience. On behalf of organizing committee, so I would like to apologize. Okay. We already 30 minutes past, so I will start my talk straight away. Okay. So before getting to my talk, I would like to introduce briefly where I come from. So I'm from Swansea City. In the right-hand side, you can see the United Kingdom map. So especially I'm from the shadowed area. It's called Wales country. So I'm from Wales region. The Swansea is located here. It's approximately 3 hours journey from the well-known city London. Okay. The left-hand side, you can see the a bird eye view photography of the Swansea city. Especially, I marked here our two campuses. One in Singleton, quite old, is 100 years old, and this year we are celebrating our 100-year century. Celebration. And the second one is a brand new 5 years old Bay campus. It's worth 400 million, funded by European Union. So if you get a chance to travel UK, please visit our Swansea University campus. If you need any further details about what are the courses available in undergraduate, postgraduate, and research programs, please visit www.swansea.ac.uk. Okay, so let me give a short introduction about what is the proud or the some of the interesting factors of Swansea City. So our own research and innovation started historically in the 1842. You can see in the history of fuel cell was discovered by Sir William Robert Grove. He was born in Swansea. And of course, the right-hand side top, you can see the panoramic view of the Swansea city. Okay, so we have a beautiful beaches around the city. And of course, this is again the top view of our Bay campus. And particularly the airroad area, this is where my research lab is located in this building. It's called multifunctional photoelectrocatalysis and coding. So, okay, what are the contents today I'm going to talk? So I'm going to talk the two parameters. One is the solar catalyst, the semiconductor, and the solar energy or sun, and then how you can create the impact in a clean energy, particularly producing hydrogen fuel generation. So three keywords I'm going to talk. One is semiconductor, solar energy, and hydrogen fuel. And what are the fundamentals in solar catalyst-based hydrogen fuel generation? And what are the challenges in this field or in this subject, and what are the recent progress, and how the field can be moved to the next direction. Okay, so I conclude with future outlook. So again, a snapshot on my what I'm doing in my lab. So basically, I'm a material scientist and material physicist. I'm working on to establish a platform for advanced nanomaterial processing and analysis, especially for constructing a cost-effective solar energy conversion system for applying in a diverse range of application. Mainly, I'm focusing on globally challenging issues, for example, energy demand, environmental cleanup, and healthcare application. So mainly our research group working in two major areas. One is the synthesizing materials and then applied in a device fabrication, particularly on proof of concept. Then in associate with our industry partners, so we are transferring the technology from lab to market. So this is what I'm doing in Swansea University. And the bottom of the slide, you can see what are all the applications we are working. One is the solar energy conversion to the electricity and solar energy based fuel generation, particularly hydrogen fuel. And third one is the water cleaning applications. Okay. So why this topic is important? Okay. As you see in any of the major cities these days, the day by day the utilization of the transport is increasing. So this will create a huge energy demand. You can see the recent survey of global oil demand, and on the other hand, so we are heavily using the fossil fuel. So these fossil fuels are highly creating are highly polluting the environment. If you take the statistics of the source of the carbon dioxide emission, so the transport is approximately 13%, is one of the major contributor to the environmental pollution. So the current fossil fuel resources are, it's slowly depleting. Okay, so we don't know what will happen in after 10 years or 2050 or next century. Okay, so in order to keep in order to overwhelming these parameters, one is the energy demand and environmental pollution, as well as how to manage this in future. So this is the time to think about to develop alternative energy resources. That energy source should be pollution free, sustainable, and renewable. Okay, so what is the what is the answer for to address all these parameters concurrently? So the one answer is solar energy, because solar energy is inexhaustible, it will be a renewable, it is a pollution free. So why we can't go for solar energy? Okay, so before that, why we go for solar energy? So in theoretically, if you see in every day in the earth, you can receive a huge amount of solar energy on the earth crust, particularly 10,000 times that energy is larger than what you consumed per day on the earth. So it's approximately the total volume is 2 into 10 power 14 kilowatt. In the hand, 10,000 times excess energy is available. Okay, so why we can't utilize this excess energy into useful way, particularly solar to hydrogen fuel generation. And particularly the India is a highly blessed country in the earth. So one of the highest solar irradiation compared to Western countries like the UK or any other northern part. Okay, so India is an appropriate place to conduct this kind of application. Okay, so before going to the any kind of solar energy application, you must understand the absorption nature of or the you understand the solar irradiation spectrum. In physics word, I can say it is a simple absorption spectra of solar spectrum. Okay, you can see here. So this is the wavelength versus normalized solar intensity. So as you know very well, the light can be classified in three region. One is the UV, visible, near infrared. So if we observe if we record the solar energy absorption, so this is the resultant spectra. You can see a huge amount or the larger amount of light photons, it falls on the visible region. Okay, so compared to UV is very less amount. And of course, near infrared, the red shadowed area also approximately 50%. Okay, so if you want to go for solar energy conversion application, connecting with the material science or semiconductor, so your material should absorb the solar light harvesting, particularly in visible wavelength region. Okay, but unfortunately, the most of the solar to hydrogen fuel generation is working very well in UV region, but it's not feasible for applying in an outdoor solar light driven application. So ideally, if you choose any type of semiconductor for solar energy application, that should be in between 1.1 electron volt to 2.8 electron volt. Approximately, it can be absorbed as solar light harvesting in between the 400 to 800 nanometer from the green area to almost slightly cover the red shadowed area. So this is the very primary thing you should understand if you go for a solar energy application through semiconductors or material science. So when the vision started, I mean, how the idea comes, the transforming the solar energy to hydrogen fuel. Okay, so in the nature you can see any plants, they produce their food only using two parameters. One is the light, that means the solar light, and water. Okay, so only using these two parameters, sunlight and water, it produces their own food, glucose, and it emit the oxygen as a byproduct. Okay, I can consider this byproduct will be a fuel. It's a cheaper fuel, right? So this is called natural photosynthesis, with producing their own food and emitting oxygen gas. Imagine that if we can replace with some artificial semiconductor instead of these natural plant leaves and produce the oxygen gas using the same two parameters, sunlight and water, it will be awesome, right? So this is the idea of how the transforming the solar energy into hydrogen fuel. Yes, of course. The idea was, groundbreaking phenomena was discovered in the year of 1972 by Professor Fujishima and Professor Honda. So I'm proud to say that I was working with him. And this is the setup, okay? So simple two electrode electrochemical cell, and then they replace with titanium dioxide single crystal and applying the solar light in the water, okay? So it oxidizes the water and produce the oxygen. And this can be called as an artificial photosynthesis because it's the same, it's very resembling, the natural photosynthesis process. Of course, why hydrogen? Hydrogen is a zero emission energy carrier. So, and also storing chemical energy from the solar energy compared to the battery or any other system, it's very cheaper and it'll be affordable. So this is the reason we go for solar energy to hydrogen conversion. So is it feasible come to the market? Yes, of course. But it already the hydrogen is one of the main feedstock for the fuel cell. So hydrogen fuel cell based transport system already implemented around the world. You can see in the picture in the slide, not only a small car, a big truck and train and buses. In recently the South Korea implemented the hydrogen fuel powered buses in the road. UK already introduced several years ago, and of course we are expecting this kind of train in UK in 2022. Okay, so anyone can think that yes, of course, in the daytime, the solar light can be transferred to the hydrogen generation. So what will happen in nighttime? So as I mentioned, these part of the hydrogen can be utilized for the transport application, for example, like a fuel station. Okay, and the nighttime, these kind of hydrogen, store it and then send to the electricity generation feed into the fuel cell. So a clock hour, these solar hydrogen storage can be applied in the transport system as well as the electricity generations. Okay, now the question is how much volume, the demand of the hydrogen supply, how much volume we can generate from this solar hydrogen technology, okay, especially through photoelectrocatalysis. So that is a big question mark. Okay, so I'm going to cover what are the recent progress and fundamental and challenges. Okay, so now I get into the fundamentals, how it will work. Okay, so I'm going to compare before getting to the photoelectrocatalysis. Okay, so forget about this word photo. So I would like to, what is the electrolysis or electrocatalysis based water splitting? Okay, so imagine that you are taking the TiO2 photoanode is here, and then it connected to the cathode like a platinum. It's a simple like a battery, okay, anode and cathode. So if I want to understand, what will happen under the sunlight, okay, then I will check the simple IV plot or applying the small potential in the circuit, what will absorb the current density in the circuit, okay. So in the electrocatalysis point of view, okay, so if you're applying the potential, so you take at least a minimum potential, onset potential to produce the oxygen evolution on the photoanode, okay. So see the current density is drastically improved after certain potential, okay. So what happened in the cathode side, it produced reduce the protons into H2. In the IV plot, you can see in the negative potential side, after a certain potential, it start, it's giving a high amount of current density. So the overall, you can understand that splitting water H2 into O2, you need some minimum potential in between the OER, the oxygen evolution reaction and hydrogen evolution reaction. Okay, so this is the minimum potential to drive the water splitting by dark condition, the electrocatalysis process. Okay, so what will happen under the sunlight or any other light-driven catalysis? Just imagine that the sunlight is fall on the photoanode side. So now you can see even in a small potential, you get a minimum, your good amount of photocurrent density in the circuit. Okay, it producing the oxygen evolution on the photoanode compared to the electrocatalysis. It drastically we reduce the applied potential, so you consume a lot of input energy. Okay, so of course there is no change in the cathode because it doesn't change anything in the cathode side. So, but overall, when you compare the electrolysis and the photoelectrocatalysis, these much large amount of input potential is drastically or significantly reduced applying the light energy. So this is why we go for a photoelectrocatalysis or any other light-driven catalysis process. I can say these light-driven electrocatalysis process can reduce the minimum applied potential for overall water splitting process. So now the question is, what kind of semiconductors are feasible, or any other restriction to apply material in the water splitting process, especially photoelectrocatalysis? Of course, the physics and chemistry people can understand this figure like a semiconductor material, the corresponding band gap energy, the extreme left side. This is with respect to vacuum, and this will be converted into normal hydrogen electrode to the electrochemistry point of view. And there is you can see a window, dotted line here. This will indicate, whenever the semiconductor, this is conduction band and this is valency band. Whenever the conduction band portion of the semiconductor above this 0 NHE position, it can reduce the water, the proton into hydrogen. Whenever the valency band semiconductor position is highly positive than the 1.2 volt, it can oxidize the water into oxygen or OH minus to oxygen. So this is the primary condition, thermodynamical point of view, the requirement of band gap energy position of semiconductor towards the water splitting process. Okay, so this is the idea how you can convert the vacuum scale to normal hydrogen electrode scale. Okay, in the law, this is not a new technology. Of course, from 1972, people have started to work on a different configuration. So I can make it in a two-way solar water splitting. One is the indirect way. That means the solar photovoltaic cell based electrocatalysis, just powering, you take a external power from solar panel and then make a water splitting by electrocatalysis method. This is the indirect methodology. So another one is the direct methodology. That means the electrode itself, working under the solar energy and then oxidize or reduce the water into hydrogen and oxygen. So this is one way is a wired configuration. Make it, you are applying a small potential in the circuit. This is called photoelectrochemical. And another one is a photocatalysis. That means no wired configuration. So the same material, you can put it in like a powder form or coating form, no any external potential applied in the circuit, and it under the light condition, it produces the oxygen and hydrogen. This is called photocatalytic water splitting. So today I'm going to talk about only photoelectrochemical point of view. Okay, so but in theoretically there are three ways available for transferring the solar to hydrogen fuel. Okay, so how does photoelectrocatalysis work in a lab scale? Okay, so imagine that this is the simple like a battery. Okay, so this is the photoanode and this is the cathode, platinum material, and in between the anode and cathode, it's separated with the Nafion membrane, so it's conducting only proton. And in between photoanode and cathode, we are filling the water, simply water, or any other highly conducting electrolyte, and it is connected in the circuit. For your understanding, I just draw the absolute scale with respect to the band gap of the semiconductor. Okay, so now you can convert it to the how much it's theoretically, it equal to the normal hydrogen electrode. Okay, anyway. As I told, whenever the conduction band above this kind of required potential, so it can reduce the water. If the valence band is highly positive than the 1.23 volt, it can oxidize the water. Okay, now the story starts. When I apply the sunlight irradiation on the semiconductor, it first produces the photocharge carrier, photoelectrons in conduction band, and photoholes in the valency band. Okay, so as I mentioned earlier, these photo holes, highly thermodynamically powerful, oxidize the water because the valency band portion is above 1.23 volt. So what happened? So it oxidized the water and produced the byproduct H plus, and this H plus is a from this anode compartment to cathode compartment through the naphthalene membrane. Okay, and what will happen these photoelectrons? So I'm applying the reverse potential here. So it's scavenging or pulling out the electron to the circuit and go to the another terminal cathode. So now the gentlemen photoelectrons are waiting in the cathode, ready to reduce the water like H2O or H plus to H2. Okay, so this is a simple phenomena, the photoelectrochemical water splitting in the lab scale. Okay. So how it will work? I don't know whether my video is working or not, but due to technical problem, I will try it. Okay. So the left hand side, you can see a double electrode chemical cell, photoelectrochemical cell. Okay. The left hand side, I can show you. Already I mentioned, photoanode or the semiconductor is placed here. Okay. And the right hand side is the cathode compartment. The platinum wire is there. In both anode and cathode, separated with an naphthalene membrane is here. And this is the circuit, I'm connected to the laboratory for measurement electrochemical station or the outside circuit. Okay. The simulated solar light is, the light is coming from here. Imagine that this is the sunlight. Okay. Sunlight source. Okay. Now I'm going to show you a small video how it will work. Okay. So now under the dark, okay, no applying the sunlight, nothing will happen. Especially watch here in the right hand side, the cathode compartment, any bubbles are coming. The bubbles are indicating the hydrogen fuel generation. Okay, so the yellow color one is the semiconductor electrode. Okay. So now I'm playing the video. You can see the bubbles are, after the applying the light, the bubbles are start to comes from the in the cathode compartment. Okay, so this is the simple laboratory scale water splitting, under the simulated sunlight. Okay, I'm going to summarize again. So unfortunately in the market, the TiO2 is titanium dioxide is the well-known material to work on the photoelectrocatalysis process, but it's working only the UV region. Okay, but we really need a small bandgap semiconductor. But sometime what will happen, the conduction band portion may not appropriate for your hydrogen evolution reaction. But positive point, the valency band may be suitable for water oxidation. So no worry, you can choose this as a OER material, the oxygen evolution reaction material. Sometimes some of the semiconductors are really favorable for the the conduction band above the zero. It will be good for hydrogen evolution catalyst. So what we can do in theoretically, so you can use this kind of material for photocathode, and these kind of materials you can use as a photoanode. So this is the basic understanding how to choose the material in this field. Okay, so now I will go into the how to evaluate your material in lab scale. Okay, so now I'm going to take two material. One is the titanium dioxide semiconductor nanoparticle and gadolinium rare material doped titanium dioxide. So first, what we'll do in a primary point of view, how to analyze in a simple lab scale photoelectrocatalysis process. So make it this material as a coating on the substrate, conducting substrate. I put it in a photoanode. As I mentioned, cathode is a platinum or any other metal substrate. So as I mentioned, this is a voltage versus current density graph. I just convert it into the normal voltage to the RLHE value. That is means a normal to hydrogen electrode value. Okay, and under the dark, no current density or no current produced in the circuit. That means no catalysis process happen in the cell. So when I apply the light, first, when I'm just comparing the TiO2 separately and gadolinium doped TiO2 separately, you can see this is the resultant graph. Okay, results in the IV. You can go into the deeper, the TiO2, comparing the TiO2 that is indicated A and gadolinium doped TiO2 is indicated B. You can see a difference between these two electrodes. So what is the difference? Okay, there are several reasons. It may be these gadolinium doped titanium dioxide may have a high conducting property or high light absorption property or many other properties. Okay, I will explain in coming slides. Okay, so this is the first step. You have to study applied small potential in the circuit and measure the current density. Okay, and next one, the chronoamperometry mode in an electrochemical station. That means you are measuring the current density in the circuit in a fixed applied potential. Okay, So if the current density generation for over the period in hours or some 30 minutes or 1 hour or 24 hours, if it is stable, it means your electrodes, it's highly stable. Otherwise it may have some corrosion problem or any other issues. Okay. So this is the second one for testing your stability of electrode using the chronoamperometry. And of course, you can measure the gas amount, how much hydrogen gas is producing in your cell. You can collect the gas and then put it in a gas chromatography or any of the so many methods are there, but gas chromatography is much easier. Okay, it will give you the direct quantity, how much hydrogen evolution from your cell. So at least if you are working in photoelectrochemistry, you must quantify how much amount of hydrogen fuel produced per hour per centimeter square. Per centimeter square means the electrode area. Okay. So this is the, you have to compare in dark and light. Here you can see a simple comparison. In dark, no hydrogen fuel, but applying the light due to the photoelectrocatalysis process, you get the more amount. After adding the gadolinium and the titanium dioxide, still the hydrogen fuel rate is significantly promoted after the doping. So this will give you an overall idea how your doping material working in given semiconductor or electrode. So I would like to repeat, first you test with IV and then stability and then gas chromatography. These are the fundamental process. So how to, qualitatively evaluate your performance is out of 100% how it will work. So that is, very typically you can compare to the efficiency of solar cell. That means input 100 light photons come from the sunlight and how much the overall 100 light photons converted into your target application, electricity or fuel. Okay, so that is here we are going to convert solar to hydrogen. So I can call it as a solar to hydrogen efficiency. There are two ways you can qualitatively evaluate your material. Okay, one is if you know the photocurrent density from your circuit, you can use this formula. Okay, apply your photocurrent density and then you can calculate it. And if you know the amount of hydrogen fuel generated from your cell, you can put into this, utilize this formula. You can, you can put the value here, the rate of hydrogen production, and then you can finally get the solar to hydrogen efficiency. So both formulas are accepted in this field. Okay, so based some labs, for example, most of the physics, they doesn't know how to handle the chemical engineering area, especially gas chromatography. So most of the physics and material science people are utilizing this area, and most of the chemists, they are utilizing this one. Okay, so anyway, so according to the NREL, okay, National Renewable Energy Laboratory America, the standard, at least your photoanode or photocathode, the semiconductor catalyst material should perform at least a 10% or above solar to hydrogen efficiency. Then it is eligible to bring to the lab to free market stage. Unfortunately, the most of the 80 to 90% or even 95% of the semiconductor shows a very small efficiency. For example, 0.1 to 1% efficiency. So now the issue is how to promote or enhance the practically what's the practicing now from the 0.1 to 10%. So I'm going to talk next few minutes, next 20 minutes about this one, how to promote from the lab scale of 0.1 to 10%. So what are the challenges first? Okay. Imagine that a ball like a semiconductor, your photoanode or photocathode, or like a nanoparticle immersed in the water and under the sunlight. So three parameters. One is the semiconductor immersed in the water and sunlight. What will happen? Okay. First case, your semiconductor material should have a high light harvesting ability under the sunlight. This is the first requirement and first challenge. Okay. The second one, every semiconductor under the light irradiation, as soon as it produces the photocharge carriers in conduction band and valence band here, okay, it drastically recombine together. That means it loss, it recombine together. So what we have to do that immediately we have to pull out the photocharge carriers outside, okay, in the targeted site. For example, photoelectron to the charge collector and photo hole should go to the electrolyte. It's more like a tug of war, if you can achieve this one, definitely you can get a high efficiency. And another one is a surface defect. There are a lot of semiconductor, every semiconductor have own surface defect, for example, in terms of oxygen vacancies or sulfur vacancies. Okay, so how we are going to deal these kind of surface defects? sorry for the interruption. So I can see someone's mic is on. If I have time challenge, please let me know. Okay, time restriction. Okay. The final point is how the photo. When you are working a long duration, your material may subject to corrosion, either chemical or photo irradiation. That's called a photo corrosion or chemical corrosion. So these are all the challenges, when you are applying this material in a photoelectrochemical water splitting. Okay. So now I'm going to summarize the the overall what's going in this field. Okay. So to try to achieve the solar to hydrogen efficiency about 10%. The first one, people are concentrating the new type of advanced material, how to enhance the visible light from the sunlight, and assembling co-catalyst materials, try to enhance the catalysis process. And platinum is expensive, so try to inventing new type of material which should be a low cost. Okay. And second one is the process point of view, how to enhance the charge separation. As I mentioned, the photoelectron photoball, make it in a very speedy charge separation. And another one is how the photoelectrons are transported to the charge collector. And third one is the system side, of course, the self-driven PEC fuel cells without applying any external energy in the circuit. And of course, the new avenues are how to hybrid the photovoltaic or any other secondary source connected in the PVC cell. And of course, the another one is the sustainability. Even though your material demonstrate less efficiency, that doesn't matter, but your material should show a long sustainability. That means a stability. Okay. So people are working on the passivation layer or protecting layer to make a long durable performance. And final one is a alternate feedstock. So if you are using a pure water in your application, water splitting, it definitely will affect the food chain. Okay. So people are now they are applying, try to implementing the biomass or any other pollutants, water pollutants, seawater, instead of pure water in the electrochemical cell. So these are all the area what we are working in the field. So in the literature point of view, you can see the quantum efficiency with compared to the different materials in terms of light absorption and the quantum efficiency number. There are most of the material shows in the UV based materials are high performance quantum efficiency. Unfortunately, if you go for a solar light driven material application, very few materials only shows these efficiency under the 10. So there is a ample space here. You can see that how to achieve the more than 10%. Okay, there is a new materials. So we try to, if you want to work in this field, please think about this one. Okay, this is a starting point. If you want to, what type of material you have to apply in this area. Okay, to achieve high efficiency. Okay, I will shortly. I already 30 minutes over. I will next 10 minutes, 10 to 12 minutes. I will show what are the recent progresses going around the world in this field. So our own report, on how to applying the nanomaterials, especially nanowire, vertically aligned nanowire, and then introduce a hierarchical type of tree-like structure, nanorods, how it enhance the light harvesting, and then it promoting the photocurrent density. You can understand the spectra right now. Okay, so V versus I, V versus J. Okay, so here this is the black color one is the KO2 nanowire. After introducing kind of branches, the current density is increased. That means something happened, after introducing this kind of hierarchical nanostructure compared to the conventional vertical nanowire. Okay, the another point, is we published in few years ago, how to make a high charge separation photoelectron and photovolts by introducing the highly conducting graphene oxide scaffold attached to the TaO2. Okay, so compare the photocurrent density here. So the compared to the bare TaO2, the graphene oxide TaO2, it particularly, I think I can compare here. It make a drastic change. Okay, this is another idea. And I will another area is going to introduce the co-catalyst material. That means that we're adding some secondary material to the primary material. Okay, so for example, this is the primary photocatalyst or photoelectrocatalyst material, and these are all the co-catalysts like metals or metal oxide or anything. Theoretically, thermodynamical point of view, if you compare the reaction coordinate and the enthalpy like del G, so the only photoelectrocatalysts consume a high thermodynamic energy. After I introduce some kind of supporting catalyst material on the surface, it's significantly reduced from here to here. Okay, so if we compare to the, excuse me.
Thank you very much.
So if you compare to the potential versus current density, okay, so you can see this is the without co-catalyst, okay, this is the plot is here. After introducing the co-catalyst material, it significantly shifted from the high voltage region to lower voltage region. So it indicates that when you are assembling the co-catalyst material on the surface of the primary semiconductor, it reduces the thermodynamical energy and lowering the applied potential. Obviously, you can save a lot of energy in the circuit. So there are plenty of co-catalyst material reported in the literature, but one review I would recommend by Professor Jaramillo group in USA. Please note down this literature. Plenty of material they tested in acidic condition and base condition. You can choose the best OER, I mean oxygen evolution reaction co-catalyst and hydrogen evolution reaction co-catalyst material. Okay. Then another one report we introduced how the interfacial charge separation layer introduced the primary semiconductor and secondary semiconductor. Okay, it's like a sandwich layer. Okay, so the tungsten oxide bismuth vanadate is one of the best sandwich structure, heterostructure in photoanode area recent days. Okay, but still there are surface states happening, existing in between the WO3 and bismuth vanadate. It may affect the charge transfer from charge transport or charge transfer injection from the secondary layer to primary layer. So what we did some metal doped in the secondary layer. That means tungsten doped bismuth vanadate, for example, and then we inserted in between the WO3 and bismuth vanadate. So eventually it created a step type like a pattern. Okay, it's like in physics point of view, type 2 energetic structure. Okay, so instead of the flat energetic structure, these kind of steps facilitate the photoelectron injection very rapidly from the point of injection to your charge collector area. Okay, so obviously you compare the only bismuth vanadate and WO3 bismuth vanadate without interfacial layer is here, the green color, the C, indicated C. After inserting the sandwich layer, I mean the interfacial layer, that's the current density is drastically improved. That means something is happened or promoted in the water photoelectrocatalytic water splitting process. So this is the one example. And of course, another area is going how to replace the platinum, expensive platinum. As you know very well, platinum is expensive than gold, what you're wearing in your ornamental. Okay, so you definitely restrict bring the laboratory to the market. So how to replace this platinum with a cheaper semiconductor material? The one way we are introducing the photo p-type photo cathodes. So it perform the what the platinum is doing, the proton to hydrogen, the same performance it can do. It's like a water reduction. Okay, otherwise you can use the same, keep the photoanode and just replace the platinum. Okay, this is the novel idea. You can introduce the completely replace the platinum in the water in the water splitting cell, photoanode and photocathode. So it's a cheaper one. Okay, so this is the one idea. And in this point of view, we recently reported a few years ago, and you can see the photoanode front side and photocathode is the back side. Okay, it's like a sandwich structure. So this is the conventional platinum paste. So we just remove this Nafion membrane and everything, and then put one small artificial leaf type structure, put it inside here, and then we tested the water splitting process. And you can see here, compare the platinum and our proposed titanium dioxide coated with cadmium sulfide and molybdenum disulfide. If you want to see this material in a naked eye, so you can see the high resolution transmission electron microscopy. You can see this is the inside is the titanium dioxide. A small quantum dots size to 4 to 5 nanometer is coated on the outer surface of the titanium dioxide. And you can see some of the molybdenum sulfide here. It's a 1T structure, okay, a sheet-like structure, MOS2. This is a dark catalyst. So this overall TiO2 cadmium sulfide MOS2 structure acted as a photocathode. Okay, so we are just completely replaced our platinum wire, platinum cathode. So still it's working very well and shows a feasible or comparable hydrogen evolution performance. Okay. The problem is, as I mentioned, if you go for a long photo irradiation, imagine that is a photo anode or cathode. So it may went to this out, the top layer maybe went to corrosion. So in order to overcome this problem, so now researchers are developing kind of stable photoprotective layer coated on the photoanode or photocathode. Okay, so I would like to compare a recent report by Professor Journal Group. Okay, so they coated with the ALD, that means atomic layer, deposited a very thin titanium dioxide layer on a well-known P-type gallium indium phosphide. Okay, gallium indium phosphide is highly corrosive if you put it in the water for under the long light irradiation. So what they did, they just coated with the protective layer and they check whether this protective layer may reduce the performance or it retain the performance. Okay, I'll go there directly. Simply go to the stability test. Okay. Here, the red color one is the bare gallium indium phosphide. That means without any protection layer. It's initially it shows a very high photocurrent, but it drastically, it's reduced and go. So the black color one, they coated the titanium dioxide protection layer. It show a very stable performance, but very, very less photocurrent. Okay. So this is a kind of negative effect, even though it protects the surface, but obviously it affects the performance. Okay. So what will happen? So they coated again the co-catalyst material. You can see in the cartoon, okay, the yellow color or the green color. They coated a co-catalyst material, organic-based co-catalyst material on the top of the layer. So see, this is the negative axis. Okay, don't confuse it. That from start 0, from the high number is here. So after the coating the co-catalyst on TiO2 layer, drastically increased green, and here high photocurrent density but in a stable performance. So from these studies, what we understand that even though if you go for protective layer coated on the primary water oxidation or water reduction catalyst, you must need another co-catalyst material in some cases. Okay, please keep in mind. So very recently this year, a few months ago, my group and Professor Sanger group from Yogi Vemana University, Andhra, they are amazing group in material chemistry. They developed a capsule shaped photocatalyst material. That means a cadmium selenide. So they developed the titanium dioxide passivation layer. It's protected, highly protected. So we tested this system, how this titanium dioxide protecting the photocatalyst material in hydrogen fuel generation. So you can see it's a huge amount. It's a really, really good amount of hydrogen fuel is developed in a different thicknesses of titanium dioxide. Okay, this is another example how the protecting layer will help long radiation against the photocorrosion. Okay, the recent days, a new type of architectures are going instead of as is shown in the photoanode and cathode in separately. So now they are applying solar cells directly, and then they coated a water oxidation catalyst on one end, and they connected as usual the platinum cathode. They put it in a water splitting cell. So why they introduced the solar cell? Solar cells have a high efficiency in a charge separation point of view, as well as the light absorption. So this will help to drive the water splitting reaction more effectively than the direct photoelectrocatalysis process directly on the electrode. Okay. This is another one example. See here in the system, this is the three junction solar cell here. Okay, and the yellow color one is the water oxidation layer coated here. Okay, and sorry, the three junction solar cell is in brown color, and it attached with the water oxidation layer and connected with the platinum layer. So this is the one good record and one good demonstration. And another one, the solar cells and coated with the water oxidation layer in the front end and back end coated with hydrogen evolution catalyst, and they remove the circuit. It is called a monolithic structure. Okay, so the one good example. So this is the solar cell, gallium indium sulfide and gallium indium phosphide, and front end they coated with the ruthenium oxide. Please be careful, understand that this doesn't work with under light. This is a dark cat. They utilize the solar cell. Overall, the monolithic is showing a very good performance. So recently, most of them heard about Perovskite solar cell, one of the champion solar cells coming very rapidly. The efficiency number is progressively started from 5 to 21, 23, 24, So, but one problem, if you apply the Perovskite solar cell in the, it's not stable in water or humidity. Okay. So what recently one of my colleagues in my department, Professor Tristan, and in association with Bath University, UK, they demonstrated they coated the like a carbon, mesoporous carbon, they coated on the perovskite structure protecting the perovskite layer, and then coated with, as I mentioned, some kind of co-catalyst on the top of the layer, and they demonstrated the current density, the photoelectrochemical water splitting. Okay. So there are so many structures or these days reporting with perovskite solar cell or tandem structure. See here, they're connecting with different type of structures you can see. Okay. But keep in mind, whenever you make a modification on your surface, additionally, the complication is added. Okay, see, the only stable semiconductor, and when you are adding the kind of material top and bottom, the complexity, device complexity increased. Okay, be careful that. And this is the overall report, so far the efficiency reported in the literature. You can see refer the number. Okay, it's currently almost 19.3 to reported by Caltech, USA, and NRL is reported in the year 2017. I think now the recent report says that it across the 20 nowadays. Please refer the recent literature. And if you go for a lab to free market, keep in mind 3 parameters. Not only efficiency, your lifetime of the electrode is very important. The cost for scalability, if you are improving from the millimeter to the centimeter to the meter. Okay, so these are the very important. I would recommend this review. Is a very amazing review by Professor Jason Lee from South Korea. They discussed different points involved in the scale-up area. Okay, please refer this literature. And another suggestion, what we are, this is give an overall idea how the system complexity versus efficiency. Okay, as I mentioned, the photovoltaic cell-driven electrocatalysis cell show a very high efficiency. Practically, solar to hydrogen efficiency about 10% to 30%. But problem is it have a high device complexity. In the case of photocatalyst, without any applied potential powder type, it is very, very low system complexity. But problem is it shows a very less efficiency, 1% or less than 1%. So in the case of photoelectrocatalysis, I shown here last 30-40 minutes. So the performance is in between the photovoltaic driven electrocatalysis and photocatalysis. This give you a positive idea, positive view. You can manage the system complexity and balance the efficiency. So if you want to work in photoelectrocatalysis, please keep in mind the practical solar hydrogen production is far away. Okay, we are in standing in at 10%. Okay, still if 10% is not easy. Okay, so if you want, please keep in mind the number and the challenges. If you want to come, please go through the strong literature and then more concentrate on your material. Okay. Many of the reports from India, I have seen photocatalytic dye degradation. It is appreciable for understanding the subject point of view, but in reality, we need to move in practically in another application, like a water splitting hydrogen generation or water treatment in different type of chemicals or chemicals in the new type of application. We have to move on. Okay, so I want to share here. And of course, almost 45 minutes finished when I started, after I started the presentation. So I want to give you a few take-home messages. So one is of course, the solar energy materials is a promising candidate. Either it is an absorber or catalyst, particularly for solar fuel generation. But the important thing, you should understand the energetic structure of the photoelectrocatalytic material. Then only you can promote or enhance the solar-driven catalysis process. And of course, the stability point of view, before and after the reaction, you should investigate your material, how it's stable, or if any corrosion is happening on your material. And as I mentioned, we try to think about new type of applications of including fuel generation, chemical synthesis, and extra. And keep in mind, more attention required for reactor design without hydrogen or oxygen leakage. Charge transfer characteristics, how the photoelectron or photoholes are injecting or transfer from your semiconductor to the targeted end. And of course, you should evaluate the apparent quantum yield. That means how it transfer out of 100 light photons to the fuel generation. And taxonomy from the lab to free market. So most of the report shows only the directly efficiency and material performance. But in practical, we should know what are the hidden parameters involved in your lab scale work For example, how much money involved, how much cost incurred your process. So this is very important. And of course, if you are working in another area, solar photovoltaics or windmill or any other battery area, this is a good application. You can connect your secondary source and water splitting or make a collaboration. And we are currently working in utilizing the waste, like pharmaceutical waste, um, metal mine waste. We put it in a photoelectrochemical cell, and then we are developing hydrogen generation. So this is give a highly new idea how transforming the waste to wealth. So I would like to introduce about our next course. As the organizer mentioned that I'm establishing the platform to help the rural Indian students. It's called ANEH Conference Series and ANEH Foundation. So we are going to start a fundamental and advanced course for nanomaterials area for different application. So the course will jointly develop and conduct by Manonvi Sundaran by next couple of weeks after in associate with Manonim Sundarnar University, Tirunelveli. And please visit www.aneh.in. So the registration already started. So you can get all the information in the website. Okay. So please pass this information to those needy or your friend circle. Yeah. So the speakers are coming from the eminent institutions like IIT, ISER, and NITs, okay, and other reputed state universities. So please visit our website, and if you have any query, please write the course coordinator, Dr. Sabrinathan here, sabrinathan@msuniv.ac.in. Of course, I would like to, this is the time to thank my collaborator and my student, Miss Catherine Davies and Ben Johns, and other my specific colleagues. And of course, I would like to acknowledge all funding agency and our Indian and abroad overseas collaborator. And these are all my funding agency. So at this in this stage, I would like to stop my presentation, and I'm happy to answer all your queries. The organizer suggests me they are bringing the questions from the YouTube to here. Okay, so I'm going to stop my sharing my presentation, and please feel free to interact if you have any queries. Okay, thank you very much for your patience. Hello. Okay, use of hydrogen in vehicles is good, but when accidents, so that explosive is problem, how to overcome. Okay, thank you very much for Bhavi Kumar. And of course, hydrogen is explosive and petrol also explosive. Okay, so every, even mobile also, during the charging, it may explode due to the battery issue. So that's not a prime point to restrict application. So we need to think how to make a very safer utilization of hydrogen, because the advantage, as I mentioned, hydrogen is a carbon dioxide free carrier. So if we can implement hydrogen powered vehicle, we can significantly manage the environmental pollution. That's the positive part. That's my answer. Thank you. Please.
Thanks, sir.
Yeah.
I think we have no more questions, sir. Since we are
Okay.
running out of time, I think we can conclude now.
Okay,
I
thank you.
invite Dr. J. Murugan to give the vote of thanks. Thank you, sir.
Thank you so much.
As good afternoon to all. The roots of all goodness lie in the soil of gratitude and appreciation. On behalf of the Department of Science, St. Joseph College of Engineering, the vote of thanks for the successful completion of the international webinar on solar to hydrogen fuel generation. First and foremost, we would like to render our great special thanks to our most respected chairman, St. Joseph Group of Institution, Dr. B. Babumandaran sir, for his constant encouragement and providing a stimulating environment for such educational developments. We feel happy to offer our heartfelt thanks to Managing Director, Mrs. B. Jessipriya ma'am, and the Director, Mr. B. Sashi Segar sir, Principal Dr. Vadi Shashirao sir and Dean Dr. B. Parvatini madam for their support towards this event. It is my bounden duty to convey my thanks to our head of the department and the convener of this program, Dr. V. N. Nadini Devi ma'am, who has been the driving force behind all phases of this program. From the depth of our hearts, we thank our invited speaker, Dr. Sudhagar Pitchaimuthu, who accepted our invitation besides his busy schedule and enlightened the sessions with his thoughtful lecture. We feel the purpose of the webinar has been accomplished. I am happy to express my thanks to all the participants from various parts of the nation and the world for their ardent positive response to our invitation and a distinct participation. I owe my affectionate thanks to all my colleagues and the organizing committee for their support, timely help, and cooperation. Once again, thank you all very much.
So thank you so much for the opportunity. Okay, shall I leave?
Yeah, thank you, sir.
Thank you, ma'am. Thank you.
Thank you, sir.
Yes, sir. Thank you, sir. The dear participants, kindly fill up the feedback link which is posted in the chat box. If you have filled up the feedback link, we can wind up the session now. Participants, I request all to fill the feedback link which is posted in chat box. If you filled up, we can wind up the session. The dear participants, I have posted the feedback link several times. Even now, I am posting it. Please fill it up.
அவங்க விளையாடுறமா நாங்க உங்க சிட்டிக்கு இருப்பாங்க உங்களுக்கு இன்னைக்கு மாட்டீங்கன்னா தப்பா வந்து நம்ம கேட்டேன் உங்களுக்கு இங்க வச்சா அவ்வளவுதான் நிறைய இதெல்லாம் நீங்க தானே தரீங்க எல்லாருக்கும்
Ma'am, sir.